Hey, geometry, lesson 5, criterion for perpendicularity. It sounds like a condition somebody could have, but it's okay, it's geometry. So, opening exercise, we have a right triangle. ABC, find the missing side. This one's all about the Pythagorean theorem, right? So, we get a leg, and the hypotenuse. And we can figure out what AB is just by doing the Pythagorean theorem. Let's see, AC, so 9 squared plus 12 squared equals C squared. Some calculator action there, and we can see that C is 15. How about if AC is 5, that's a leg, and AB is 13? That would be a hypotenuse. Everything still works, we're just trying to find a leg, so hold on. So for that one, we see that B, which is a leg, is 12. And then the last one, if AC equals CB and AB equals 2, what is AC and CB? So we're just going to say that A squared plus A squared, because they're equal, equals 2 squared. 2a squared equals 4. A squared equals 2. A equals the square root of 2. So that means that AC equals CB equals the square root of 2. What I'd like to point out here is our hypotenuse, which is AB, is always the biggest measurement of every, let's see right there, of every triangle. So the hypotenuse is always going to be the longest side, right? So if that's 2, that is bigger than the square root of 2. Just want to refresh our memories on that one because it'll be helpful as we go through the lesson. All right, there's a few other refreshers that actually aren't in your classwork, but we're going to go through them together. So Mrs. Stevens asked the class to prove the triangle with sides 5, 5 square roots of 2, and 5 is a right triangle. Lena says the triangle is not a right triangle because 5 squared plus 5 squared roots of 2 squared is not equal to 5 squared. I'm just going to write out what she says. So 5 squared plus 5 square roots of 2 squared is not equal to 5 squared. Let's do some math. I've got 25 plus, this is going to be 25 times 2. And it's true, these are not equal. So 25 plus 50 is not equal to 25. Is she correct? What do you guys think? Well, Lane is actually not correct because her math is wrong. What I just said with the last slide is the longest measurement is always the hypotenuse. Always. So if Lena wanted to figure out if it was a right triangle or not, she has to set up the Pythagorean theorem correctly. So I need the shorter legs to be A and B, and the longer leg to be C. So here we have 25 plus 25 is 50. If I square this, I get 25 times 2, which is 50. So this is actually a right triangle. You just need to, as you check your math for it being a right triangle or not, the longest leg always has to be your C term in your Pythagorean theorem, because the C is your hypotenuse, which will always be the longest leg of your triangle, the longest measurement. Sorry, not the longest leg. Okay, another random question that's not in your classwork. AC equals 4, AB equals 7, and BC equals 5. Is the triangle a right triangle? If so, name the right triangle and justify your answer. So I'm going to grab the longest measurement here, and that's going to be my C term. The shorter measurements will be the B terms, and we need to see if this is a true statement. We're going to do the math and double check. I just squared everything. And then 16 plus 25, let's see that. No, my math is wrong. 11, 2, 3, 4. 41 is not equal to 49. So no, it's not a right triangle because the left side is not equal to the right side, right? Okay. Another random question. Plot the following points on a coordinate plane. Let's see, I have some positives and negatives, so let's put my x and y axis here. And I'm going to plot the points. 0, 0. Love it when it's at the origin. So easy to find. 6, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And negative 2, 3. Negative 2, 1, 2, 3. Is this, oh gosh, is this a right triangle? Never trust my drawings because that looks awesome. Is it a right triangle? So first I constructed ABO. Let's see, OA. How will we know? Do you guys think it's a right triangle? Do you think maybe that's your right angle? Who knows? How can we determine this? How do we figure it out? Well, we need to find the length of the three sides. And you guys start moaning, no, Miss Carly, I don't want to do the distance formula 3 times. Well, you guys can do it. It's not that difficult. So there are the 3 segments that we need to calculate. All right, how about you guys watch and I do it for you this time? Because I've already calculated them out, so I'm just going to write them down. I've got OA is the square root of 52. AB is the, let's see, square root of 65. And OB is the square root of 13. All I did was use the distance formula. X2 minus x1 squared plus y2 minus y1 squared. Take the square root of the whole thing, right? So let's check it. Which one of these values is the largest? I'd say that one. That's going to be our C term. And then our A term and our B term. Square root of 52 squared is 52. Square root of 13 squared is 13. And the square root of 65 squared is, yes, 65. 52 plus 13 is 65. That does equal 65. So this is a right triangle. AB is our longest side, so that's our hypotenuse. So we guessed our right angle correctly. Pretty awesome. So angle BOA is 90 degrees. Triangle, and it doesn't matter how we name the triangle, we'll just do the same way, is a right triangle. Cool. All right, let's get into the problems that are actually on your classwork. Use the grid on the right, plot the points. I've got 0, 0, negative, or 3, negative 1, 1, 2, 3, negative 1, and 2, 3, 1, 2, 1, 2, 3. There we go. That's beautiful. Determine whether OP and OQ are perpendicular. Support your findings. So how are we going to do this? They don't look perpendicular, but remember that never is a reason. How about we use, let's see, we can do the slope of each line. That's what we sort of talked about last lesson, isn't it? And we can also do the distance formula, okay? Just like we did in the last problem, just on the last slide. Let's just do that and calculate the lengths of our sides, OP, PQ, and OQ. What are the lengths of them using the distance formula? Let's see, I get OP. 3 minus 0 is 3. Negative 1 minus 0 is negative 1. 9 plus 1 is the square root of 10. Let's do OQ because that should be an easy one too. 2 minus 0 is 2. 3 minus 0. So I get, let's see, 4 plus 9 is 13. And then PQ, not quite as easy. These numbers up here. So 3 minus 2 plus negative 1 minus 3. Let's see, 3 minus 2 is 1, negative 1 plus negative 3, negative 4. So 17. There we go. That was painful. Sorry. So let's see if it's a right triangle. That's our longest side. So a squared plus b squared equals c squared. I have 10 plus 13 is not equal to 17. So no, this is not a right triangle. Correct? So if we go back to the problem though, it's asking us to determine whether they're perpendicular. OP and OQ. They can't be perpendicular because triangle OPQ isn't a right triangle. Angle QOP is not a right angle. Therefore, those two sides are not perpendicular. That was QO and P. Okay. You could have also figured out the slope of QO and the slope of PO to see if they're opposite reciprocals of each other, but we did it by distance formula. All right, another example. This is sort of fun. In this example, we developed the general condition for perpendicularity between two segments. This one's really important because this is how we're doing the rest of our classwork. I set the groundwork for a few slides. Now we're getting to the meat and potatoes of everything. So we have our points. We're trying to find a general condition for perpendicularity. Just between two segments. It's always between two segments. I really like that my endpoint is always at the origin between two segments, and we'll get to another example where we do that. But I'm going to refer to triangle ABO. Here's my triangle. Okay, what must be true about triangle ABO? What must be true about triangle ABO if segment OA is perpendicular to segment OB? Okay, what must be true about triangle ABO if those two segments are perpendicular to each other? We just did the distance formula on the previous slide using the origin, and it was super easy. The distance, getting the length of this segment, we basically just did a squared plus a1 squared plus a sub 2 squared, the square root of it. And then this segment, we did the same thing. To find the distance of this, or the length, it was really easy because we're going back to the origin. It was like b sub 1 squared plus b sub 2 squared, the square root of all of it. So to find those lengths is super simple, isn't it? All right, rewind. Ask the question again. Refer to triangle ABO. What must be true? Oops. Goodness. What must be true about triangle ABO if segment OA is perpendicular to segment OB? So refer to triangle ABO. What must be true about triangle ABO if segment OA is perpendicular to segment OB? Well, triangle ABO would be a right triangle. That's what must be true. Triangle ABO would be a right triangle. Duh, of course it would. If we've got two segments perpendicular to each other in a triangle, then it would be a right triangle. So if it's a right triangle, it would satisfy the Pythagorean theorem. Oh. All right, so does this satisfy the Pythagorean theorem? Let's find the measurements of all of these sides, OA, OB, and AB. OA. So we're going A1, A2, back to the origin. So A1 minus 0, quantity squared, plus A2 minus 0, quantity squared, correct? Now OB is point B back to the origin. We're going to do B1 minus 0, quantity squared, plus B2 minus 0, quantity squared. Cool? And then this last one. AB is not quite as neat and easy. AB, hypotenuse. So we're going to do B1 minus A1, quantity squared, plus B2 minus A2, quantity squared. Those are the distance formula ones that nobody likes. Cool? So we have our distances. Now, actually, I'm going to get a new slide. Hold on. Now using the Pythagorean theorem, let's see what happens. The Pythagorean theorem says squared plus OB squared equals AB squared, correct? All right, let's plug it in. Square root of A1 squared plus A2 squared, quantity squared, plus square root of B1 squared plus B2 squared, quantity squared, equals, oh, I'm out of space, going underneath, B1 minus A1 quantity squared plus B2 minus A2 quantity squared, quantity squared. Well, you know when you flat out square a square root, the square and the square root cancel each other. So I get A1 squared plus A2 squared plus B1 squared plus B2 squared equals B1 squared minus A1 squared plus B2 squared. Oh, no. My bad. Erase that and that and that and add this and that. Phew, that was a little messy. All right, I'm not done yet though. You guys remember foiling? Yeah, don't roll your eyes. I'm going to foil. Actually, I'm going to do a new slide. Pause. Okay, what I'm going to remind you of here is foiling. So that right there is really B2 minus A2, B2 minus A2. Now I'm going to foil first. B2 squared, outer, minus A2, B2, inner, minus A2, B2, and outer, plus A2 squared. So B2 minus 2, A2, B2, plus A2 squared. And then let me get one more color here. You're going to trust me that it's the same thing, just with the 2's instead of the, oh, shucks. Okay, it's all right. Sorry, those are, one of those have to be 1's. Dar, I can't redo it. That's going to be a 1. I flipped them. I know you guys can follow along though. It's no big deal. All right. So this is going to be the exact same format as this. These are the same. I'm just going to trade out 1's instead of 2's. So I have B1 squared plus 2 A1B1 plus A1 squared. I see a little mistake over there now. This should have a little 2 in it. That was painful, wasn't it? But hey, now we're going to simplify. Let me copy this stuff down here, hopefully without making a mistake. And if we've got the same terms on the left or the right, we can subtract them out. So I'm going to do an A1 squared and an A1 squared, A2 squared, A2 squared, B1 squared, B1 squared, B2 squared, B2 squared. 0 equals negative 2A2B2 plus, oh, should that be plus? That should definitely be minus. Sorry about that. Minus 2A1B1. Okay, next I'm going to do some math magic. It's not really, but I'm going to factor a negative 2 out and write these in the correct order. So I just changed the order of the A1B1 and A2B2. Then I'm going to divide both sides by negative 2, which magically makes them disappear. It's not really disappearing. I mean, you're doing a valid division move, but it sort of looks like magic. Now, if I totally lost you in these past few slides of the whole derivation of this, just write this down, because this right here, this is what we were working for the past few lines, or past few slides. This is the whole general condition for perpendicularity. This is what we've been doing today. This is the purpose that we're here. The whole criterion for perpendicularity is right in this red box, right there. Okay? So what we demonstrated was the two segments, OA and OB, they have a common endpoint in the origin, and that's really, really important. Common endpoint. If you don't have an endpoint in the origin, you need to move your figure to the origin for your common endpoint. At the origin, which is 0, 0. Your endpoint has to be at 0, 0. And then you can use that condition for perpendicularity to test it. We're going to multiply the two values together, and if they add to 0, then you know it's perpendicular. It's pretty cool. So example 1, going backwards a little bit, you can flip back to your example 1 in your paper. Example 1, I had a triangle with a point at O, A, which is 6, 4, and B, which was negative 2, 3. Verify that it's right. Verify that OA is perpendicular to OB. Using, well, the formula we just did. So what we're going to do is we have to prove that 6 times negative 2 plus 4 times 3 equals 0. Negative 12 plus 12 is in fact 0. Okay, yes, it works. The segments are perpendicular. You have a right triangle. Also in exercise 1, we had a triangle OPQ that wasn't right. Let's verify that. I had O at 0, 0, P at 3, -1, and Q at 2, 3. So we're going to do 3 times 2 plus -1 times 3. That gives me 6 minus 3 is not equal to 0. So no. Is that not way easier than the distance formula? Yes, Miss Carly, yes it is. Very cool. All right, here's a doozy of an exercise. Given the points, the whole list there, find all pairs of segments from the list below that are perpendicular. So we're going to test OA, OB, OC, etc., etc., etc. I don't even know how to do this in the right order. OA, let's see. We need to make a list in some kind of orderly fashion, right? OA to OP. I've got 6 times 2 plus 4 times -3 is 12 minus 12. Cool. Oh, these are all segments. OA perpendicular to OW. That is because I've got 6 times -6 and 4 times 9. Cool. How about OS perpendicular to OW? -18 times 6 plus -12 times 9 is also equal to 0. And we could go on, okay? You would need to test all of these. I think you get the picture though. OS and OP, OB and OC. Let's see, OB and OC, OB and OT, those work. OT and OU. And then the last one is OC and OU. I'm not going to go through all the math. It's just simple multiplication and addition. You guys got it. Let's do one more exercise. The points given are the vertices of a parallelogram. Is the parallelogram a rectangle? Support your answer. I'm going to plot it really quick. Okay, I can quickly see that I'm just drawing triangles to check my diagonals, and it looks like all of my diagonals are congruent. So I can mark these. So I know I'm a parallelogram, right? I'm going to go ahead and erase those orange things because that's a little annoying. I could have done the distance formula on every single side length, but we all know that that's not our favorite thing to do. So I just drew the right triangles to check my legs are equal, therefore my hypotenuses, are equal. So now let's just check an angle. Remember, if I've got 2 pairs of parallel sides, then if one angle is right, then we're all right. So let's check OA to see if it's perpendicular to OC. So I'm going to check A and C. -4 times 1 plus 1 times 4. -4 plus 4 is in fact 0. So we know the parallelogram is a rectangle. Yay! Okay, this is another problem I found because I want to show you one more thing you're going to need to know for your problem set, and it wasn't in the classwork. And that's awful when things aren't in the classwork. So follow along with this last one. So here we have another problem. It says, given the points you see, prove that PR is perpendicular to QR without the Pythagorean theorem. So the first thing I have to do is actually, well, let's see if I can move this whole slide. There we go. I need to move this drawing so that one of my points is on the origin. Let's see if we can do that. So up 1 over 3. So if I'm here, I'm going to go up 1 and over 1, 2, 3. It was nice to have enough space. Oh well. And then this one is 1, 2, 3, 4, 5, 6, 1, 2. 1, 2, 3, 4, 5, 6, 1, 2. So So here's my triangle. I just moved it so that one of my points was on the origin, right? That's not a big deal. We can do that. So we see that I moved point R. Oops. I moved point R, -2, I moved it up 2 and up 2. So my new R is 0, 0. So that means I would move each one of these points. I would translate them all, correct? So I would go up 2 and over 2. So let's do that same translation for P. I'm going to add 2 and add 2. And Q. I'm going to add 2 and add 2. So now I can check my perpendicularity. Let's do 3 times -2 plus 1 times 6. -6 plus 6 is in fact 0. So it's a lot easier to translate your points and to check that condition for perpendicularity than it is to do the distance formula that many times, right? Awesome. Good work today.